Well, thanks for the introduction, and welcome everyone. So I am Guray Ozen from Google Research. So today I'm going to talk about NVGPU Dialect and how to program it, and we will program this NVGPU Dialect using the Python bindings. So this is a tutorial. It's going to take more or less like 50 minutes, 40 minutes. So hold on. And again, this is a tutorial, but it's based on a work, and this work wouldn't be possible with these people's help. So thank you so much, and their help was big. Okay, it's the last talk of the conference, so let's start with some fun things. Anybody has heard about the Huang's law? So I want to start with this. I want to understand who knows. Like, can you raise your hand? Anybody has heard Huang's law? Okay, one. No one, really? Okay, exactly. Okay, two. Good. NVIDIA guys. I didn't invent this, right? So this is a law. It's a big debate. It's a law or not. But it says, in the last 10 years, we got GPU every 2 years. And the performance of GPU more than doubles every 2 years. This is more or less true. Like, take the first GPU architecture. This is like Kepler. You had FMA instruction. Today we have Hopper GPU, even Blackwell. In Hopper, it's delivering 1000x. It's delivering 1000x speed up for int8. And this is all in 10 years. It's like insane speed up, right? And GPUs are delivering really good speed up. But the question is, can you get the speed up just buying the Hopper GPU? Well, you wish not. You don't get it. You need to change the program. Why? Because Hopper GPU came with a lot of hardware features. What are these? New Tensor Core, thread block clusters, TMA, asynchronous barriers, all of this stuff. And if you don't use them, there is no performance for you. Like, really. And using them means you need to change your software, you need to change your compiler. A lot of work. Like, how a lot? So I did some quick research in NVIDIA software. I took their PTX, it's the virtual instruction set, and I took the Cutlass. Cutlass is their open source matrix multiplication library. So what I did, I analyzed in the PTX side, the upper graph is the PTX, down graph is the Cutlass. I checked the number of instructions, increment of number of instructions, and the down is showing the increment in the code size. These two programs are increasing massively. Like, they are trying to catch up the hardware. Hardware is moving really so fast. And if you look at it, even during lifespan of Ampere GPU, which is 2 years, these two software increase quite a lot. So today we have Hopper, more hardware features, software is growing. But in this room we are LLVM people. And are we doing a good job to catch NVIDIA software stack? That's the question for you. But I'm MLIR guy. We are doing a good job. We are not bad. So in MLIR, we have implemented NVGPU and NVVM dialects. We are targeting Hopper. And by using these dialects, you can use more or less all the hardware features. It is not as good as we would like, but it is getting there. Performance is quite good, and everything we have done is upstream in the MLIR repository. So what are we going to do today? We are start from zero. We don't know Hopper. And in the end of this tutorial, we will learn NVGPU Dialect. We will learn how NVGPU Dialect is lowered to NVVM and then plus PTX. We will implement multistage kernel. And we will implement Warp specialized kernel. And we will get CuBLAS-like performance and be hero. So that is the tutorial about. Let's start. And where are these dialects? And where are we? So here is the MLIR, LLVM, PTX. And if you look at the bottom level of MLIR, you will see NVVM dialect. So the NVVM dialect is like PTX, but it's not, like little bit higher level, but almost PTX, it's like close to the middle. But on top of it, you will see NVGPU dialect, which I think is so cool. And it can talk other high-level dialects like memref, or vector, and it generates NVVM. So in my opinion, NVGPU dialect can do all the things that compiler is good at it: code gen, assembly gen, lines of code, a lot of code, but makes code readable from your point, from the user point. So it will give you the full control, and we will able to use the advanced features of the GPU. And today, where are we today? We are going to be on the Python bindings. We are going to be on top of MLIR. We are user. What we are going to do, we will decide. We will decide today how to implement our kernel. right? So here is our path. We will start from Python, go to NVGPU, go to NVVM. But, this is MLIR. It's all about, progressive lowering. And if you have your compiler, or if you want to use whatever dialect in MLIR has, you can lower this in NVGPU, and you can start leveraging, whatever we have in MLIR. So that's why I like MLIR. I mean, everything can compose, right? So that's really nice. And so this is another one. If you are a Cutlass expert, if you are familiar with the Cutlass, so Cutlass has some layers, and device, kernel, collective, atom, and thread, these layers. And we have some similarity in MLIR and Python. So if you are a Cutlass expert, take this slide offline. But as you can see, the bottom of 3 layers are in the compiler. The upper 3 layers are in the Python right now in this tutorial. Okay, let's start. And so I have implemented a tutorial, and I am about to be upstream. We are still, doing the code reviewing process. It's going well. But if you want to follow from your computer now, and you can, take this PR and then follow it. And when you get it, you will have 6 chapters. And I'm going to implement the 7th chapter. Well, we will skip the first chapter now, the Hello World. But for the other chapter, we will go, line by line. We will go line by line, and we will implement everything. And the last chapter, the chapter 6 is coming. Like, I am going to implement it later. And so again, this is a tutorial about the Hopper performance. And in order to focus on Hopper, I have implemented DSL just for this tutorial. And this DSL is going to simplify, the boring things. Again, compilers are good at it, which is called GEMM. So let's start. Here is our chapter 1. In the chapter 1, I'm going to implement SAXPY, 2D SAXPY. And in this program, we want to run on the GPU, but we are not going to use Hopper feature. We will just understand what we have today. Like what we have in the MLIR, how can we use MLIR from Python, these things we are going to learn. And here is the way how you can write MLIR in the Python. So as you can see, we are going to take this Python, and this Python is our MLIR generator. It looks like a language, but it is not. So let's go step by step. And the first step is our function. We have implemented a Python decorator. So this Python decorator is cuts the boilerplate a lot. What it does, it generates funcop in function dialect. And you can pass numpy arrays. For example, x and y are numpy arrays, but it translates them in memref. So it is MLIR now. And if it's scalar, like F32, it translates that. And when you call this from the Python, it JIT compiles and it executes the program. So we have 2 decorators. So the first step in the program, now we have function, right? This is a host function, and I need to do the basic things like copy data, allocate data, and that's what I'm doing. I'm using the GPU dialect for that, and allocating data and copying the data. And of course, in the end of the program, I copy back the data, right? So now my host program is done. Let's look at the kernel one. So for kernel, we have implemented another decorator. We have 2 decorators in total. And this decorator, you can set grid size, block size, cluster size, shared memory, everything you need your kernel. And inside of this function, it is your GPU kernel, and this decorator will generate GPU launch for you. So inside everything is in GPU kernel. And one more other thing. So you can see the arithmetic here. It looks nice. But we did operator overloading. So this overloaded to arith dialect, and we generate the arith dialect for that. Because this Python looks like a language, but it is actually everything is an MLIR value. So this is an MLIR generator. So it was so easy to do operator overloading and get the arithmetic. And so we can implement SAXPY in this way, because we parallelize. You remember it was 2D. We parallelize 2 outermost loops to thread blocks and threads. And then we have, if you look at the kernel, we have like 2 loads, and then we multiply and add. That's it, and store. That's it. That's our SAXPY. So now, that's our SAXPY. Now let's run it, right? Let's run it. I am using the numpy arrays, and I call this function. So thanks to my decorator, it translates everything to memref, which is cool. And if you want, you can recalculate the same thing on the host. You can verify it. And then hopefully when you do Python chbound.py, this is going to pass. And it's passing. Okay, so now the chapter 2, let's go on the Hopper. So now we know everything, how does DSL work, how MLIR work, how we can generate, the MLIR ops from Python. Let's do the Hopper work. Let's do the SAXPY, but let's do SAXPY with TMA. What is TMA? TMA is this yellow thing in SM. It can load data asynchronously from shared memory to global memory. Right? And it can do address arithmetic, it saves your register. It's really cool if you can use it. So we will use DMA to load data. And to do this, we have implemented 3 ops, and we have implemented 2 sets of ops in NVGPU Dialect. And the first set is the TMA one. And in the Python side, in our DSL, we implemented a nice class. It does the boring things again, the type generation, casting, all of this stuff. We hide it inside, so input code will look nicer. But it's actually MLIR generator. It's like one function generates one MLIR NVGPU op. So let's go one by one. And the first one is create descriptor. So in order to use TMA, you need to create a descriptor on the host. And this descriptor needs to know everything about your data, your device pointer, how much data you will load in one load, and then swizzling, L2 cache, everything. And then the second one is prefetch. Now you create a descriptor. If you are accessing in the loop, you want to put in the L1 cache so it is faster to get. It's for the optimization. And the last one is the load. So you have a descriptor, you want to load the data, right? And as I mentioned before, TMA is asynchronous. So this is the second set of ops we have implemented in NVGPU Dialect. And these are the mbarriers, asynchronous transactional barriers. So we will use TMA ops as a transaction, and we need to assign an mbarrier for this to wait the transaction. Right? And we have the mbarrier mechanism for this. So again, we have implemented the ops, and this is the Python class, which is the, to simplify the code. Let's go one by one. What is high level in the NVGPU Dialect? So for example, create, which is super cool. You can create like multiple mbarriers, and it returns to one SSA value, right? But in this SSA value, you have 7 barriers in this example. And if you want to use it, in init, arrive, or try wait, you can access it with another SSA value, like you are accessing in an array, and which is really cool because if you are doing things in the loop and you are probably using multiple mbarriers, so you want to access it with the induction variable or something. So it's really nice. Another nice thing, all the ops in NVGPU Dialect supports predication. PTX supports predication. LLVM doesn't support predication. But LLVM doesn't support Hopper anyway. We generate everything. We generate all the codes here through inline assembly. Like we generate PTX in the MLIR. So we can support predication. I don't see any performance benefit, but it keeps my code nice because I don't need to generate SCF if, or like if statement, which is, I think, cool. Okay, so let's go back to SAXPY, and let's start building the host IR. And the host IR part is the same like before. The only difference is we need to create a TMA descriptor, and we need to set what is going to be the size of the load. In this example, every thread block will compute 32 elements, so my each load will be like 32, right? So that's what I am setting here. And I am doing this in the host. So now let's see what is the generated code. It generates, NVGPU op that we implemented. What happens with this NVGPU op when you lower it? It lowers to the runtime. In MLIR, we have a runtime, small runtime. And this runtime calls to CUDA driver. CUDA driver, we pass everything from Python NVGPU to CUDA driver. And then we pass everything. So you have like full control. Again, swizzling, strides, box, padding, L2 cache promotion, everything we pass in runtime. And then it returns our descriptor. And then we finally copy this descriptor to the device using mem alloc and a mem copy. And then we return you the device pointer you can directly use in your GPU code. Okay, now let's build the GPU IR. Computing of SAXPY, it's same as before, but the way we load data is significantly different. Let's start. It's our first step again. We will do initialization. We have like bootstrapping. And in this bootstrapping, I will need one mbarrier. I create my mbarrier class. It generates the mbarrier create. I need one of them. And I need to initialize this barrier with one thread. Because TMA is asynchronous again, It doesn't waste any registers. I will select whatever the thread I want, and it will request TMA to load data. That's why I need one thread. And this op is predicated, right? Because only one thread needs to run. And for sake of simplicity, this thread is the thread 0. But we have implemented other mechanisms that you can select the fastest threads, but not in this tutorial. OK, let's do the TMA part. And in the TMA part, again, we are loading. We use the load function. We need to calculate where are we going to load in the shared memory. That's the only calculation we do. And then these classes will generate a TMA load. TMA load is also predicated, right? It's also predicated because only thread 0 will do it. And then in the end, I run the mbarrier arrive because I have to say my thread arrived here, right? And my transaction count is 256, which is the size of x and y. So that is I am assigning this transaction with an mbarrier. First thread is assigning this. And of course, after this, I need to weight that, right? I need to weight this mbarrier with the try weight. So try weight generates that NVGPU op, and if, as you can see, this is not predicated. So all my threads are weighting data from TMA. And after this, my data is ready, and the computation is same as chapter 1. OK, so now let's go to another chapter, chapter 3. In chapter 3, let's do a little bit more advanced things, math pool. Let's use Tensor Core. How do we use it? I select this size, which is a nice tile size. We will use it. But in this program, we will do only this size. We will do only the small size, and we will launch one thread block, and we will offload all of these 3 loops to the Tensor Core. And again, in order to use Tensor Core, we have implemented NVGPU ops. These NVGPU ops are only for the Hopper GPU. I don't know Blackwell, but it's not going to work on Ampere GPU. These are new ops, and they are supposed to work with Warpgroup level. What is Warpgroup? Warpgroup is 4 warps is Warpgroup now. Right? It has to be run by Warpgroup. And we have the 4 ops. Like first op is initializing the accumulator. What is accumulator? Well, if you look at the Tensor Core, the operation is not matmul. The operation is matmul and accumulate. So you need an accumulator. If you don't have it, which is fine, you still need to use this op. This op is going to generate register for you and assign it with 0. Yeah, that's fine. And the second one is the generate descriptor. So Tensor Core works with the descriptor if you are loading data from shared memory. And this descriptor is 64-bit integer, and it's super annoying to create this because every bit keeps something else, and you need to do a lot of shifting. To save you, we have implemented the op, so it does everything, and to generate the descriptor. And the third op is the MMA. It does the MMA. It uses Tensor Core. The last op is the store. You have the accumulator now. You have the results register. It stores in the wherever you want, shared memory, global memory. And again, we have the Python class for this. We hide the complexity there. And we did also operator overloading. So let's look at the code. In code, everything will be more clear. And let's start with the host IR. And the host IR is like similar to SAXPY. You allocate data, you copy the data. What is difference is the TMA descriptor creation. Because now I want CVSLing, and TMA can do it. Right? And for CVSLing, I'm selecting I want 128 by CVSLing. Nice. And my A matrix is 128 by 64. That can be my TMA load size. TMA can load everything at once. Fine, nice. But B is a bit different. Because the contiguous dimension of B is 128, and which is 256 bytes. It doesn't fit on my cache line. It is not my CVSLing size. What do I have to do? I have to chop it up. TMA cannot load this. This is not my limitation. This is TMA limitation. And I have to chop it. I have to split B into 2. So we will load B in 2 parts. We will generate 2 loads to load B. First part will load 64 by 64. Another load will load another 64. Right? This is a B1 and B2. That's why we are setting the tile size, the load box size of the B64 and 64. So let's implement the GPU kernel for that. Here is the GPU, our entire GPU kernel to multiply the matrix. And again, the first step is the bootstrapping, initialization. We create an mbarrier, and then we initialize this one thread. This is predicated, all good. Now let's load the data. To load data, we have implemented TMA load function in Python. So we will use this function in next chapter, probably in the next chapter. So keep it in mind. And what this function does, it calculates the offset on the shared memory for matrix A and B, and it generates 3 loads. Right? Why 3 loads? 1 load for the A, 2 loads for the B. And it can also do the coordinate calculation, because you need to tell TMA where it's going to load from the global memory and where it's coming to the shared memory. And this is doing that. It is also dividing the B into 2. So in the end, we will have this function is going to create 3 TMA load and then 1 M barrier arrive, right? Your barrier will arrive. Okay, and then now let's multiply the matrix. We weight the data, we load the data, we weight the data. Now my data is in shared memory. I have everything I need. I can multiply the matrix. I need 3 things, A, B, and C, which are A, B is the input matrices. They are the descriptor. And I use my nice class again. I give the shared memory offset, and this nice class generates a descriptor for me. So these are A and B. For C, I don't have an accumulator in this program, but I still need to generate it. And I still need to generate an NVGPU op, and this op is going to initialize my accumulator with 0. So the multiplication is here. We multiply F16 by F16 and accumulate on F32. Right? That is the op. And in the end, lastly, if you see this line, this is the multiplying the matrix, because we overloaded the operators. It generates the NVGPU Warpgroup MMA, which multiplies your whole matrix. And I hope this code looks readable, because in deeper, many things happens. And this many things is because your matrix is so large, your tensor core cannot multiply that big matrices. It's too big, right? So this op hides the complexity of PTX, and it makes things readable. It can multiply things in tile size, but in the end, it simply like lines of LLVM code. So what it does many things. First thing, it selects the good shape that tensor core has, and it splits your matrix into the tiles, right? This is one thing. The second thing, most of the time, if your K is big, you probably accumulate on the same part. Like look at the first 4 of them. You are accumulating on the same part. Or this one, you are accumulating on the same one. So you need to use the result of the first instruction, look at like W1 in there, as an accumulator of the second instruction. Right? That's basic. But are this code running sequentially? No. This code is not sequential. These instructions are asynchronous. So what this op does, it collects them and then commits them. And then hardware is probably going to run in a parallel way or some concurrent way. I don't know, but it's definitely not sequential. So what this op takes care of it. And another one, of course, it iterates over the small tiles. So that's how you can see plus 128, plus 256, all of these things. And in the end, in the highlighted box, it waits, right? These are asynchronous operations. It waits all of them. It waits tensor core to be done. And then your data is ready in registers. Your data is ready in registers, and these registers is the C. But these registers are fragmented. Right? They are fragmented, and it's given by the hardware. So to use this, to store this fragmented data, we have implemented another op, which is store. It can store these fragmented registers to shared memory or global memory. We hide this complexity from user. Right? User doesn't have to know what is this thing. But if you use the store, it is going to store in a fast as possible way. It will do the swizzling. It will use advanced instructions such as SD matrix. It will do everything. This is one way of solving. Today there was another talk talking about the vector layout. This is another way of solving. But this is one way. Okay, so we have implemented matmul, right? We are using TMA. We are using the swizzling. We are using all of this stuff. So the question is, if we parallelize this program across thread blocks, and if you put a loop, is it going to perform? What do you guys think? Is it going to perform well? Actually, I put already I want performance. It is not going to perform. It is not going to perform because it's not going to perform. Your tensor core is so fast, you have to feed it. And you cannot feed it because you have a bottleneck. You are using the TMA, it doesn't matter. TMA is not increasing the bandwidth is the same. TMA is saving the registers, right? That's all it does. So one technique to solve is multistage, software pipelining. It's an old compiler technique. So what do you do in this case? You use more shared memory, and you load your data ahead of time. And when you are in that instruction, that iteration, your data is probably ready because you loaded previous iteration. And so here I am illustrating. So every color is the slot, and I split program into 3 parts: prologue, main loop, epilogue. And in the prologue, I start loading the data. This is all asynchronous anyway. I don't wait. And then when I come to main loop, I do MMA, and then after the MMA, I am loading the TMA. I'm loading data with the TMA. So I overlap data load with tensor core. That is the technique. So this is the next chapter, chapter 4. And here is our GPU kernel. Right? We have prologue function, we have main loop function, we have the epilogue function. Let's go deeper. What is prologue? This is our entire prologue. I have a SCF4. And in the SCF4, I am using the TMA load, which I showed you before, and it does the TMA load. And then we continue. This is asynchronous, right? I'm not waiting. I'm just telling thread 0 to go tell TMA to load data, and then continue. And then we start the main loop. So you can ask, what is main loop? Like, what is the main loop? That's the terminology. So let's look at the tiled matrix multiplication. We have 6 loops. First 2 loops I parallelize across thread blocks, and they are gone. They're gone. They're parallel. I don't have it anymore. And the last 3 loops, you remember, that is our tile size. It is gone on the tensor core. What is left? What is left is the damn K loop, right? It's sequential loop. That is the main loop. And to do this, of course, to implement this, that is my main loop. IR, by the way. I am using the SCF4. And one more thing, this K loop, using the same accumulator. Every iteration is, iterating over the accumulator. So the accumulator is the iterargs in for-up or like loop carried variable, right? We accumulate over the same accumulator. That's why we need to use as an iterarg. Okay, now let's go inside this box, inside this main loop. This is the inside the main loop, my whole IR. And again, let's go step by step. So our first step, this is a multi-stage kernel, right? I have multiple slots. And our first thing is to understand what is my slot. It's very easy to do. You do, induction variable modulo by number of stage. There you go, that's your stage. And then you need to wait the data, right? Because you started loading in the prologue or you are loading in the main loop. You need to wait this data to be ready in the shared memory. And after this, you can start. So here is the first step. And another step to multiply the matrix. Now our data is ready. And for this, we have also we are still using the WGMMA matrix class in Python. But I created these matrices, outside of my loop because my matrix traits are the same, right? It's the same swizzling, everything is the same. The only moving part is the shared memory side, is the shared memory pointer. So what I do, I update the shared memory offset for A and B. And D is the accumulator. As I said, it is the iterargs. So I have to use the accumulator from the previous iteration. So that's the iterargs. So that's are my A and B and D. I can multiply the matrix. That's it. We multiply the matrix. What is next step? Next step is the TMA load, right? I need to keep loading the data. So because this is the multi-stage kernel, I need to keep loading the data, and another iteration, and the next iteration, my data is probably ready. So what I am doing, for example, here, I am loading the data for the first slot, the blue slot. Why? Because I already did in the first iteration, right? This slot is done. I use this data. I use this slot, so I can do it. And in the next iteration, I will use another slot. Oh, that is the multistage. So we are overlapping we are overlapping tensor core and the data load. Okay, so that is the epilogue part. Now I multiply the matrix. Everything is good, but they are in the shared memory. Let's do it in the fastest way. The fastest way is not to copy your registers to global memory right away. No, that's not perfect. What you have to do is you need to store in the shared memory first. And we have a special op. It does swizzling very fast, and no bank conflicts. So, which is the fastest way. And then after this, your data is nicely in the shared memory. You can copy this data to global memory in a coalesced way. Right? That's the perfect way to copy data. That's the perfect epilogue, at least for this example. Okay, so now let's talk about the performance. I mentioned that, single stage, the previous chapter is not good, and the multi-stage is important. So how important? These are the benchmarks. So what I did, I took one shape, it's a 7K, 256, and K. First two dimensions are the same, and the K is different. Why K is different? Remember, main loop. When you have more K, you have more main loops, so you can understand what is the importance of using multi-stage. And we are doing the same operation, F16, accumulate on F32, cool. And the tile size is the same tile size, 128 by 128 by 64. Everything is the same. So, okay, look at the graphs. The first graph is showing K is very small, 128, and the last graph is showing K is very large. When K is very small, you don't have a loop, so using multi-stage, there is no multi-stage to use. There is no effect. But when your K is large, you have more loop, right? And then you can understand the effect of multi-stage. So these graphs are showing the teraflops, and higher is better. And look at also the x-axis, we are showing the stages. We have maximum 7 stages because that is the end of the shared memory. And if you have like one stage, when your K is large, you are getting more or less 200, 180 teraflops, right? But when you increase the stage to 6, 5, your performance increased to almost 400 teraflops, which is 2x. Insane, right? It's a big win. So you must use multi-stage. There's no single stage program. Okay, so are we going to be hero? Yeah, maybe. Let's look at the performance with CuBLAS. CuBLAS is amazing library. It's out of the box, gives you performance day 0, which is nice, and implemented by performance, engineers. A lot of team behind this. So here is the performance difference between our poor chapter 4 against CuBLAS, and we don't know what CuBLAS is doing. We don't know the tile size. It's a very close source. It has own heuristic. But in MLIR, we are still doing the same thing. We still have the same tile size. That is the performance of our chapter 4. I am again showing the teraflops, and in there, so higher is better. Blue is CuBLAS. Chapter 4 is red. And that one is the matrix shapes, the shapes of the matrix. So if you look at here, it's not so bad. And for some shapes, we are similar to CuBLAS, but for some shapes, CuBLAS is like significantly better. But here, we are good for that chapter, right? And yeah, again, for other shapes, CuBLAS is doing pretty well. It's almost like, 40%, maybe 50% performance. So they are good. What are we gonna do? And we will go to next chapter. In the next chapter, this chapter is not going to give you the performance, but we will learn the concept. So in Hopper, we got warp specialization. This is the technique I learned from Cutlass. And in this technique, we are going to specialize the warps, actually warp groups. What is warp group? 4 warps is one warp group. We are going to specialize it. And in this chapter, we are going to launch 2 warp groups. In the previous chapter, we launched only 1 warp group, right? Because we did everything in warp group. In this chapter, we are going to launch 2 warp groups, 256 threads. And here is the illustration. Let's look at it. The first warp group will be the producer. It's going to do data load. It's going to only load the data. That's it. And I'm going to reduce its registers to 40, 30. It's not going to use any registers. Right? I'm going to just, make as easy, simple as possible, this warp group. But the another warp group it is going to be the consumer. And I'm going to increase its registers to, I don't know, 230, 40 something. So I'm going to give everything, whatever I have in the SM. And what's it going to do? MMA. It's like just going to use everything, all the compute power in my warp. Right? That is the concept. And I'm going to use the mbarriers to synchronize them. Right? Because the blue MMA has to be done. So the producer one can start another TMA for that multistage. Okay, that's coming. And yeah, okay. So here is our kernel for the warp specialization kernel. We have implemented other classes and Warpgroup class. This class is very basic. You need to select the primary thread of your Warpgroup. And as we have two Warpgroup, first primary thread is 0, another one is 128, right? And you also need to select the register size. How many registers you want to use? And then after you create these Warpgroups, you can use the with keyword in Python, and this with keyword, you can access this class. What is this gonna do? It looks nice. So inside this blue box is going to be your producer's code. Your producer Warpgroup will go there. What we are gonna generate, we will generate just SCF if, right? That's how you do code gen. And inside, we will reduce its register size to 40 here for the producer. And if you look at the producer, it will do only the TMA load. That's really it. On the consumer side, so this the red box is our consumer side. Everything in this region is going to be our consumer Warpgroup, and it will do the MMA. Consumer loop is doing the MMA, the K loop, remember? And in the end, it does the one epilogue. So how is going to be the performance? Here is the performance again. Now we have new chapter, and the new chapter's performance is not even good. Like we are not yet there. It's not perfect. And it's not perfect because we know this is not going to give our performance. But what we learn how to do warp specialization. Right? We learn how to do warp specialization. This is important. So how we can get more performance. Right? We want more performance. We want more performance because CuBLAS has. I can also have it. I mean, the technique is there. We can generate the code. Well, this is the next chapter. It is coming. Stay tuned. And I don't have it yet. The idea is Ping-Pong. It is the persistent Ping-Pong warp specialization. And this terminology, I didn't invent it. I take from Cutlass. Cutlass is the best. I reverse engineer that to implement MLIR. That's the only way I think you can do compiler in these days for NVIDIA GPU. Anyway, in this program, we are going to launch 3 warp groups. And the first warp group is going to be our producer again. It's just going to do, load. That's fine. But another 2 warp groups are going to be our consumers. Right? The consumer ones are going to do the work. But the key point is here, when one consumer is doing Tensor Core, another consumer is going to do the epilogue. So does it make sense? Well, look at the SM, right? Look at the SM. What are you going to see? You will see TMA. You will see Tensor Core. You will see arithmetic logic unit. They're different. So if you use them, at the same time, and you can get really good performance. And that is the key of this, the key idea of this program. One is going to do the epilogue, another going to do the TMA, and another one is going to do the Tensor Core. So again, this is going to be, I don't have the code yet, but it is going to be easy to implement with using our Python and with using our Python class. Well, that's already it. And that is the end of the tutorial. And you will have the codes online. And what we have learned, we learned that MLIR is great. We have the dialects, NVGPU, NVVM. And we unlocked the Hopper's power, right? And we unlocked Hopper's power. We have implemented multistage. We have implemented warp specialization. And that was the picture of today, right? We are the Python bindings. We are the user. We have full control. I know shared memory. I know my barriers. I know my warp groups. I know I can decide. I'm the user. I have full control. I used the NVGPU Dialect. That's the compiler. And it did only the boring things. Code gen, assembly, like lines of codes. That's just, we don't want to do it. Somebody has to do it. And then we lowered to NVVM. And NVVM didn't go to LLVM because LLVM doesn't have open support, and we directly generate the PTX assembly from this. So, well, that was it, and I hope you enjoyed. Yeah. Thanks, everyone.
Okay, any questions?
So can you do like element-wise or like some reduction after you do the MMA? Or is it like, I don't know much about the Tensor Core, like do you have to move from some other register?
Yeah, let's go to that slide.
Yep.
So we can. We can do everything. Well, why we can do everything? Because we can hide, we are doing it. We hide these things in the Python, and in Python we go to NVVM, dialect, and these are actually registers, so we can do the reduction. Mm-hmm. We can do whatever we want. But we don't have a good methodology, a good ops, or good things to do this in the, in the NVGPU dialect yet.
Okay.
So yeah, if you and I work together, I think we can do it. We can do it better.
Thank you.
Yeah.
I have a question.
Yeah.
So in terms of the expression here, is this much more compact than describing it the way Cutlass describes it?
Well, I have a layer comparison with Cutlass. Let's go back there. I have a lot of slides. Yeah, this one. So, I mean, we are kind of replicating the Cutlass here, but it's not our intention. I mean, it's not that we want to write a Cutlass. It's just this layers match. And Cutlass is written in the CUDA, and here we are using half of it, we are using compiler, and another part we are using the Python. So in the end, they are doing the same thing. Is it easier? I think Python is easier than going Cutlass.
Any other questions? Okay, please thank our speaker. And